This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello everybody, good afternoon, and welcome to our final week at Algorithms for Functional Genomics. Oh, I'm going to miss you. Yeah, thank you for enduring me for the first 11 weeks. We reached our final one, and on this one, we have a very special and trendy topic on supervised learning. And before we start, just a reminder of a previous announcement is that the Subject Experience Survey is online, available for this semester. It closes up on Sunday, the 3rd of November. If you haven't completed it yet, please do as soon as possible. That's very, very important for subject coordinators to make sure we keep improving the courses as well. So if you have any idea, any suggestions, we're happy to bring them aboard. Constructive criticisms are more than welcome. And you can find more information online on how to fill this up as well. So we're going to talk about supervised learning. But before that, just a quick recap on what's learning. I think on week 4, we started talking about unsupervised learning. And specifically, we talked about clustering. And this week, we're going to talk about classification, regression, and how do we go about to evaluate, in a very robust way, our methods and predictive models we develop. So what's learning? So humans learn by experience. And learning, according to Herbert Simon, is basically any process by which a system improves performance from experience. So what does it mean for a computer to learn? Why we want them to learn, and how do we get them to learn are the main questions we want to answer. And basically, we want them to learn because most of the time it's very difficult or very expensive to program computers to perform tasks directly. For most of the tasks, it's very, very difficult to program them. If you imagine digit recognition, so image recognition, there are a very large number of ways a number 2 can be written. And it is not always clear what the digit means. So if we have to explicitly program an algorithm to identify what a number 2 looks like, that will be a very difficult task, especially if it's written by a medical doctor, which is just a line or something like that. So it's tricky. So what we want to do is actually get programs to computers to program themselves by showing examples, experience of inputs and outputs. And we want to write a parameterized program and let the learning algorithm instead find a set of parameters that best approximates a desired function or behavior. And this function could be a mapping from a given image and saying this is character 2 or 1 or 3 and so on and so forth. So what we want to do is let the data do the work. And we want to understand and learn patterns implicit from the data. And there comes machine learning, which is a term that has been around for 60 years, coined by Arthur Samuel, which basically means that it's a new field of study, not that new anymore, but it's still in ascendance, where we study computers and the ability to learn without being explicitly programmed. So basically, for computers, experience is data. And the definition by Tom Mitchell in the late 90s is basically machine learning is the study of different algorithms and algorithm classes that has 3 basic aspects, which is, one, we want to improve performance of a given task, and we have a given task, and we want to do that by incorporating experience into the process. So a well-defined learning task will have these 3 components: the performance, the task, and the experience. And unfortunately, we will only have time to cover a few classical machine learning approaches, and we can divide them without loss of generality in 2 big groups: supervised learning and unsupervised learning, even though these days there are other categories of approaches that we won't have time to cover. Including semi-supervised and so on and so forth. So basically, the main difference between these 2, supervised and unsupervised, is on unsupervised learning, the data is not labeled, while on supervised learning, we, in advance, have the answers. Okay, so we have a categorized or numerical data. Okay? And unsupervised learn can then be divided in clustering. So we mentioned a few of these algorithms. For instance, we are trying to split data points in groups. We can do that in different ways. Distance-based, we have agglomerative, partitional, divisive, and so on and so forth. I hope you know the difference between them and the different compromises. We also mentioned a few dimensionality reduction algorithms that can be understood as unsupervised learning techniques, for instance, SVD, PCA, where the main goals are either to reduce noise, reduce dimensionality, so you can better visualize the data and better understand variability. And there's also a third set of methods on unsupervised learning that we didn't mention, we didn't cover, which is called association mining. And basically, with association, we were trying to identify, just looking at different properties of the data, associations between different features. Just one easy way to understand this, imagine you go to Kohl's or Woolworths or your favorite supermarket and you have a shopping list, right? And multiple clients will have multiple shopping lists. You can ask the question with association mining is, what are the subset of items that are bought together? For instance, you can associate rule will be something like this, that item A and item B are always bought together, and that happens 10% of the time. And when it does, it has a confidence of 99%. For instance, people that buy milk also buy cookies. Why not put milk and cookies together in the same alley? Okay? This is associate rule mining. And this week we'll focus on this side and this branch, which is supervised learning algorithms. And on supervised learning, we can broadly classify them in two groups of methods, depending on the predictive task we're interested in. First one is we're aiming to predict a category, for instance, whether a mutation is leading to a pathogenic or whether a mutation is leading to a disease or not, or a number. Alternatively, let's say you're interested in developing drugs for malaria. You can predict whether this is likely to be a drug or not, or you can predict the potency, quantifying. So this is quantitative and qualitative, okay? And when we want to predict a category, we call this task as a classification task, okay? And we want to predict a number, we call it regression. And supervised learning usually have three main components: the data, the features we are calculating from this data, and the actual learning algorithms. And the data is basically historical or experimental labeled data, okay? And the label is actually the target I want to predict. And one important thing, an important limitation on supervised learning is the data you collect and you use to train your model needs to be representative and diverse. So data collection and curation is key. You not only need to make sure that you have enough data that is representative, you need to make sure that it's high quality, because a predictive model is only as good as the data you train it on, okay? If you put garbage in, you get garbage out, basically. If you have your experimental data that is very, very noisy, most likely the algorithms will pick up that noise and model that noise as well, instead of modeling the underlying phenomena you're trying to model. Okay? So data collection and data curation and data quality is key for supervised learning. The other aspects are the features you're calculating. So the data here, I'm pretty sure I'm referring to the target I want to predict, and the features are basically the properties I want to calculate and to use as evidence to train a predictive model. So if let's say you work on an ICU, so intensive care unit, and you have a history of data of patients coming into the ICU and whether the treatment was successful or not, whether they died or they recovered, and you have different properties that you can use to say, can I predict, given the initial stage of the patient, whether it's going to evolve and to death or it's going to recover. So this is basically the sets of features you can use as evidence to train the models. And they are related, and they require knowledge of the problem. So they need to make sense, right? So if you're trying to predict whether a patient is going to survive or not coming into an ICU, it makes sense, for instance, to collect its physiological parameters, be it heart beating rate, blood pressure, oxygen, and so on and so forth. Not always will be the case that you can use everything. For instance, it might not be the case that there is a difference in age. That might be the case or not, so it requires knowledge of the problem to actually select which features are likely to be interesting to model the problem you want, to model the target data. And then you have the actual learning algorithms. And you're going to provide your target data, and that makes it supervised learning, and the actual features you want to evidence to different learning algorithms with the goal to trying to pick up implicit patterns that correlate features and the data. However, which one? And we're going to discuss here a few different approaches for supervised learning and how we choose the best one. Okay? On Friday, we'll focus on evaluation metrics to try and discover which approach is best. So the supervised learning pipeline looks more or less like this. So you have a training phase and a predicting phase. Okay? You can think about predicting phase of a finished model that is also that has been deployed and it's been used in a real situation. So what usually happens is you start collecting your data. So you define your problem. You're asking the question, how can I predict X? And you go about and collect as much data as you can, but you make sure you have good quality data as well. That's the data part. And then the following step is generating features, which is also called feature engineering, which encompasses not only feature generation, but feature analysis and curation as well. So asking the question, does it make sense to use these features, and are they related to my target or not? Once you generated the features, the next thing you need to do then is train on these features. So you basically provide, your target data with your features, and you start the machine learning, the actual machine learning process. And by that, you divide your initial data set usually into 3 that we're going to discuss. Okay? And you're going to train a specific model using supervised machine learning, and this is going to be tested. And this is usually an iterative process by which you can optimize parameters, select, include, or remove different features, and then you have your final model, which is ready to be deployed. And use then new data, for instance, new patients. You want to ask the question, what's the prognosis for this patient? And then you can make predictions using the model. And just focusing on this part, which is dividing the data set, this is quite important. So usually your data needs to be divided into 3 data sets. At least it's a good idea to do so. The first one is the training data set, which is a representative set of examples that you use for training where the target value is known. That by definition is supervised learning. You also need to have a validation set, and with the validation set, you're aiming to tune the architecture of the learning algorithm as well as estimating predictive errors. So you can think of the training set, let's say it's 90% of your data, and you're going to fit or try to identify different patterns. The learning algorithm will use it to identify different patterns, and then you use the validation set to estimate prediction errors. And you can also have a third set, which is completely separated from these two, which is an independent, it's missing a T there, independent test set or a blind test. And this is extremely important to assess the performance of the predictive model because it does it independently. Basically because we never used it during the training process. So this is completely new data we're providing to the model, and in a way it's an unbiased way to estimate something that is very important, which is called generalization. That's the main goal for supervised learning, estimate generalization. So what's generalization? Not to confuse with memorization. So what's memorization? Memorization is basically the ability to remember training data. And is that useful? Nope. No, not at all. That's not useful because that's only describes the data you've seen. The goal for supervised learning is predicting new data. Okay? So what I want to do is understand the underlying process that's going on, the underlying patterns, and be able to predict new data that I haven't seen before. So I won't see the exact same parameters, the same features, but I will see trends in them and be able to make an educated guess on the actual prediction. So memorization means I have a really good performance on training, but when I do validation and tests, the performance is very poor. Okay? So it's the inability to predict on new data. While generalization is the main goal here, which is the ability to learn from training data. Okay? And there's a difference there. And generalization will basically try to identify meaningful patterns. And that means we'll have good performance on training as well on test data. Okay? And this is the main goal of supervised learning, achieving generalization. And what happens then when your predictive model is really, really good just at memorizing data? You have something called overfitting, which is a very, very tricky problem, which is you basically only memorize what you've seen, right? Your memory foam mattress. But what about the rest? They are part of the process. They are part of the phenomenon. They are important. So we have actually two problems, overfitting and underfitting. Underfitting, or high bias, is basically when your algorithm or your model is not sufficiently flexible to make good predictions on new given data. And underfit model usually does not perform well in training or tests. So let's say we consider these as our data points, the blue dots. And they kind of look like as behaving as a quadratic equation, like y equals x squared or something like this. Well, so an underfitted model would be something that is overly simplistic. And basically this may be due to inadequate features, so feature limitation, inadequate data, or an inadequate training scheme, meaning the data is more complicated than it looks like. So this is underfitted, while the desired would be modeling it as a quadratic equation. Okay? And we can have the other scale, which is underfitting. Underfitting meaning I will have a really, really good performance on the training data, but if I then select a new point here, I won't be able to predict it well. So we identify underfitting basically when we have a bad test and training performance. Okay? And overfitting, which is a very, very difficult problem, and sometimes you can just forget about it because you're so excited about your training results. Oh, I got 95 accuracy on training. However, you might be overfitted, meaning when someone tries to use it on new data, you get a 50% accuracy. Then what's the use of that predictor? It's not useful at all. So overtraining is a very serious thing. We need to be very serious. We need to have a very robust approach in validating our methods to make sure they're not overfitted. And there are several methods even that went to the literature, were published, they are still overfitted. So it's a very difficult problem to go around. But it means then that the algorithm is trained too well on specific data sets and does not generalize. So you look at regression, we have this curve here, which looks like a senoid, right? If I try to model it with a straight line, that's basically underfitting, right? If I try to model it with a high polynomial, well, even though on training on these specific values, I always get them right, so I have the curve going through them. If I have a new data point, it's most likely going to fail to predict it properly. So what the model is doing is trying to fit on the small random variations in data set that don't actually exist. So they're not part of the process, okay? And this can result from bias on training, small training sets, over-parameterized, over-complex models as well. So we need to be very careful with this and make sure performance on training and tests are compatible. So how do I identify overfitting is when we have a large gap between train and test errors. So you have a test error that's considerably higher than a training error. Okay? That's basically overfitting. And how do we avoid overfitting? We'll discuss this during this week. Okay? So in terms of learning algorithms, there are literally a ton of supervised learning algorithms, and this depicts just a small part of those. So this basically depicts the classical learning, as we mentioned before, which is encompass unsupervised and supervised. So in terms of unsupervised, we have dimensionality reduction. We mentioned a few of those here, PCA, SVD, TSNE, and also in clustering, we mentioned K-means and DB scan. And in terms of classification, what we're going to do is select a subset which is representative of the methods available in the literature. Even though, unfortunately, we won't have time, there is a whole new set of methods which are deep learning models, which have become really popular over the last 5 or 10 years as well, which we will not cover. So we'll start with the simplest ones. And today we'll discuss 4 different supervised learning methods. The first one will be KNN, K nearest neighbors, which is a distance maze method. Naive Bayes, which is a probabilistic method. Support vector machines, and decision trees. Okay? However, this is definitely not an exhaustive list. This is basically to give you an idea of different approaches that are available out there. Okay? However, this is a kind of a representative set, even though it isn't. But it's just a subset of potential and interesting approaches. So KNN, how does it work? It's quite similar to K-means, at least the main idea. So given a set of training data, so you have a training data D, and it's represented as attributes, X, and a target, Y. So for instance, proteins, genes, or genome properties, and a target value that you want to predict. And you have N data points. And you want to test on a new point, which is X sub U. So KNN has a prediction rule that works as follows. So we're going to look at the K most similar training examples of my test point. And for classification, what we're going to do is we're going to assign the majority class label via majority voting. And for regression, we'll assign the average response. So considering this plot here, we have 3 classes, red, blue, and green, and we have a test set here, which is XU. And we ask the question, let's consider K equals 5. I ask the question, who are my 5 nearest neighbors? Out of those, 4 are red, 1 is green, therefore my label is red. And that's it. Okay? So basically, the algorithm requires a parameter K, which is the number of near neighbors to look for, and a distance function to calculate similarities between points. So the algorithm works as follows. So for each test point, we will compute the distance between the test point and each of the training points. We'll sort the distance in ascending or descending order, depending on how you implement. We'll select the K neighbors and use either the majority voting for classification or average the values for regression. Something to note here is KNN is called a non-parametric method, so we didn't have any training phase. We go straight away for testing. So it's non-parametric because unlike other learning algorithms, it doesn't learn an explicit mapping function from the features to the training, to the targets, from the training data. So there isn't a explicit model. Instead, what it does is simply uses the training set at test time to make the predictions. Right? So for instance, if we consider K1, we just identify what's my nearest neighbor, and then I borrow the label from it. And KNN, as I mentioned, requires K as the number of neighbors and a distance metric. And as we previously discussed on this subject, there are multiple different metrics. And the best one will depend on your problem. Euclidean is just one of them. And another important aspect of KNN is that features need to be on the same scale. For instance, if you have a feature that is measured, let's say, in kilocalories or Celsius degrees, and another one that is in kilojoules or Fahrenheit, you need to make sure they are compatible in order for the distance to make sense. Okay? So we need to make sure we normalize and regularize and standardize all the attributes. And then we have the problem of finding K. How do we find the best K? Since we have a parameter, we need to find the best one. We can't use one arbitrarily. In KNN, how would we find the best K? Which is something similar to K-means. We vary the K. And we can select a performance metric and try to optimize it, for instance, but always comparing test and training errors together. okay? And you can use different metrics. There are two that we already mentioned before, sensitivity and specificity, and there are others that we're going to cover on Friday. Main pros for KNN is a very simple and intuitive approach, very easy to implement, and cons, memory usage is the main one. You need to store all your training data in memory every time because you're basically not doing any training, just testing, and you need to calculate all the distance from your test set to every single point on your train set every time. And it may perform badly on high dimensions. This is mainly due to curse of dimensionality and the problem with Euclidean distance in higher dimensions, and is very sensitive to noise, as K-means is. Okay? And this is one out of 4 methods. Second method is a probabilistic one, and we already mentioned about Bayes before. And naive Bayes is a probabilistic supervised learning method, and its core is Bayes' theorem. Okay? And for a given set of features B and a class A, we want to ask the question, what's the probability of belonging to a class A given a set of attributes? So the Bayes rule will have 4 components: the posterior, which is probability of A being true given that B is true, the likelihood, the opposite, the probability of B being true given the A is true, probability of A, and the probability of B. So I can, with these 3 information, calculate this probability. So what we want to do is find the maximum a posteriori probability, which is called MAP. Basically, what we have then is a set of features and potential classes. Let's just consider classification. And basically, by doing this, we're asking the question, what's the most likely class given a set of features? So PA given B, A is my class. What's the most likely class given a set of features B? And this is basically maximum likelihood estimation, and we use Bayes' theorem to do that. Okay? How does that work? So maximum a posteriori mapping. So we want to maximize the probability of A given B for each class A. And using Bayes' rule, we can transform this into this. So probability of the features given a class times the probability of the class divided by the probability of the features. However, for each class, let's say we have class A1 and A2, probability of the features of observing those features will be the same, so we can just ignore the denominator. So we want to find the maximum value for the probability of the features given the class times the probability of the class. Is that clear? More or less? Okay. And then B is actually a set of features, right? So let's call it Xi. I from 1 to, let's say, n features. And what we want to calculate actually is the joint probability. And the main assumption, and this is quite important for a naive Bayes, is that features are independent given a class. And that allows us to calculate the joint probability. So in order to calculate the most likely class given a set of attributes, we'll calculate the joint probability of seeing all those attributes of a given class. And this is basically the product of the individual attributes given a class. Okay? So simply, we'll want to calculate the product, okay, of all individual ones. So we have n attributes. So the joint probability will be the product of probability of each of them given the class. And I want to ask the question for class A1 and A2, what's the most likely one? So the Bayes algorithm then will have 2 parts. It will have an explicit training phase, which basically on a set of examples, and for each target class, let's say we have 2 classes, and let's consider this example here, this table. So for this one, we have 4 patients with 3 potential symptoms. And the outcome is whether they're going to be diagnosed with flu or not. So they can be arrive with cough or not, yes or no, sneezing or not, fever or not. And based on these 3, we want to predict should we diagnose them with flu or not. So based on a set of examples, for each target value, for each class, meaning flu, no flu, we're going to estimate the probability of the class. In this case, we have flu appearing in 2 times, no flu in 2 times, so it's 50% each. Okay? And then for each attribute, we want to calculate the probability of the attributes given the class. Okay? And then we can pre-compute all of those. So the probability of having cough, and given that the person has flu, having cough even though the person doesn't have flu, not having cough and the person have flu, not having cough and the person has flu, and so on and so forth. We calculate all the possibilities here. Okay? And we have this pre-calculated. This is our trained naive Bayes model. And then to classify new instance, we can ask the question, well, an instance will be a feature set. And we can ask the question, let's say someone arrives in an ER, and new patients, we only cough. So cough equals yes, is sneezing no, and fever no. We want to ask the question, should we diagnose them with flu or not? Okay? And we're basically going to ask the question, we'll maximize that calculation of probability. So which class is more likely, given that the only yes we have is cough? Okay? So basically, we are going to calculate for a set of features, cough, no sneezing, no fever, whether flu or no flu is more likely. Okay? And that's using Bayes theory. And it's a very simple algorithm. Okay? And naive Bayes has been used for a long time, or not so recently, but one of the main applications it was, for instance, spam filtering. And the basic idea was, for instance, just to give an example how to use this, as you have a set of goods email, and you're basically counting the appearance of words on legitimate email, and you have a lot of spams, and you're counting the words that appear on spam. And you can ask the question, given that I have a word in an email, is it a spam or not? Let's say kitty appears here. And you observed kitty in 672 good letters, good emails, and only 13 times on spam. And you can use this information as evidence to calculate which of the classes is spam or not spam is more likely. Okay? That's basically it. So considering this as evidence. The main pros then for naive Bayes is it very easy to implement, very, very efficient as well. However, it assumes that the features are independent. So when this does not hold, you can have a drop in accuracy. Okay? So one pre-processing step for naive Bayes, for instance, is making sure your features are independent. How would you do that? Using a dimensionality reduction technique. Another good question. So, third method out of 4, support vector machines. So, for support vector machines, let's start considering that we're trying to classify points that are linearly separable. Okay? I can draw a line or a hyperplane and separate them. And for a given training data, what we want to find are decision boundaries to separate two classes. Right? So we have these points here and this point here, and we want to find a linear way to separate them. Okay? But what we want to do is to maximize the perpendicular distance between a given hyperplane and the margin between the two classes. So what we want to do is the maximum margin hyperplane. So that's the basic idea of support vector machines. And it will give us a linear separator. And what we need to find here is then which line is the best one. And we then have an optimization problem that we can solve in quadratic time. So basically finding the maximum margin hyperplane, it's a quadratic optimization problem to find the vectors w and b. So basically wx plus b equals 0. We want to find the equation of this line here. This is in 2D. However, we'll consider this in higher dimensions, so we want to find hyperplanes. And in fact, w can be found as a linear combination of training points. What we want actually are the points in the dashed line here that are along the margins of the two classes. And these are called the support vectors. So all we need to do is find them, which is something computationally straightforward. And if we have a convex function to minimize we can always find the optimal solution. So support vector machines are very, very interesting methods to work with. And it will give us a linear boundary with maximum distance between the points of the two classes. However, first thing I mentioned was, let's consider our points are linearly separable. Most of the times that's not the case. So what if the data is not linearly separable? There are basically two things to do with SVM. One is use the soft version of SVM, which is basically add a term to the objective function we're trying to minimize or maximize to penalize points that are on the wrong side. But we don't forbid them, right? So basically considering terms to penalize those points and basically giving it some slack to find the best hyperplane. And the second alternative, instead of finding a hyperplane or a line, we use a kernel function. And a kernel function will be a function that transforms your input data into a different space that hopefully will be separable. And kernel SVM will allow then for non-linear boundaries to be found. And there are several different kernel approaches. For instance, you can apply polynomials, Gaussian, sigmoids. Let's say you have this distribution of data. There is no linear, there's no way to linearly separate these two data sets. However, if you apply a sigmoid, or if you apply a Gaussian, you can then identify a hyperplane that separates them. So basically transforming the data in order to find a different hyperplane. Of course, that requires then trying different kernel functions and identify which works best for your specific features. Okay, and that's the basic concept behind SVM. And then 4 out of 4 methods, decision trees. What's a tree? What's a tree? Tree is a graph. What type of graph? Yeah? You can say it? A cyclic graph, right? And basically a decision tree will be a hierarchy of rules of prediction. And we can visualize it from top to bottom like this. So you have internal nodes with decision criteria and decision points. And if we have a binary tree, we'll have 2 children. And the leaf nodes will be the predictions or the outcome. So for instance, if you consider this tree, and this tree is modeling the questions whether a bank should give loan to a person or not, the first node would be the first decision point. Decision criteria is whether the person has a good credit history or not. If good, then we go to the next decision point, whether they have a debt over $1,000. If no, then you give the loan. If yes, then you don't give it, and so on and so forth. Okay? So it's basically a way to divide the data space. And trees can be used for both classification and regression. So our endpoints could be a label outcome or a value or even an equation. So how do we build a regression decision tree from our data? We basically can identify decision points. So for instance, a specific feature and a specific value for feature that yielding best purity. So we're going to discuss what purity could mean. Bear with me. So let's say we have a decision point optimizing purity, and then we partition the data into corresponding subsets, and we reiterate with the resulting subsets until we find a stopping criteria. For instance, let's say that the set we have is approximately pure. And impurity, in this case, in classification, would mean, for instance, misclassified data. So you're going to find the best attributes and the best value for the attributes that separates your data. And you can also consider, for instance, gene impurity, which is the probability of incorrectly classifying a data chosen by random. And in regression, you can use different metrics, for instance, mean square error. But if you look at these three, the first decision point is whether the feature x1 is less than a1. And in this case, you only have 2 features, x and x2. Okay? So the first decision point divides the space into 2. So this one, which is for values that are less than a1, and this space here. And the following one, let's say the value is less than a1, so it sits here. The following is whether x1 is less than a2. which will then divide this into two regions, this one and this one. Let's say it is less than A2, which reaches this decision point, which is asking the question, is X2 less than A4? A4 being here. If it is yes, it will define this region and will label this as R1. Otherwise, it's going to define this region, and so on and so forth, until we divide the whole searching space. And we can label them either with a class, with a categorical value, or a numerical value, or an expression as well.
So we can't scale the data here, right?
What, sorry?
We cannot scale the data.
Scale? What do you mean scale the data? You can do prior to running it, right? So the idea here is that you find decision points. This is just a way to visualize how the data ends up looking like, right? But you need to have attributes that are comparable, right? But you don't calculate a distance metric. So they don't have to be on the same unit, if that's what you're asking, right?
If we do that, then can we apply decision tree algorithm?
What, sorry?
If we transform all the features to the same unit,
Yeah.
can we apply decision?
You can still apply. For instance, let's say you only have one feature, right? So it's a linear, and you have points in a line. So you can subdivide this line into portions. Let's say your line goes from 0 to 10, and your first decision is whether it's less than 5. You divide this into two subspace, and then you say, if it is less than 5, I ask the question, is less than 1? And you define that into 2 again, and so on and so forth, right? But you do that in order to maximize purity, meaning each subset or each region will mostly be populated by one class. Yeah? Does it make sense? But you can do that with one attribute, or with hundreds of them. Yeah? So it's a very, very interesting approach, mainly because you can then interpret the tree and understand why features are important for your problem as well. So the way decision trees can divide the space is called recursive binary splitting, because every time I have a decision point, I'm dividing the space into two. And this is a greedy heuristic. When I say I choose the point which maximizes purity, I'm making a local decision. It doesn't mean will be the global option. And a prediction on a decision tree will basically be a path from the root to the leaves with features on them. And the main pros will be then, it's very easy to explain and visualize complex data with decision trees. It can help you out understand your problem and the features that are important. And you can mix up even categorical and numerical. In KNN, you can't do that, mainly because how you're going to calculate a distance from a category. Right? Like, let's say you consider gender. Let's say you consider yes or no answer. How are you going to mix that up with degrees or kilocalorie per mole or something like this, right? In decision trees, you can. And the main cons, large trees can easily overfit. So if you have a tree that is big enough, you can generate a classifier that on training is 100% accurate. Basically, each leaf will be one instance of your training set. That's not ideal. So we want to find a compromise to find generalization, and usually that's done and implemented using pruning criteria. Let's say we want to minimize impurity, but also impurity plus the tree size, making the tree as small and compact as possible. Okay? And I said there were only 4. No, I lied. There's another one. There's another class of methods I wanted to mention, which are ensemble methods, which are meta approaches, not a real method. It's a meta method, which is basically, why only use one supervised learning approach while I can combine them into multiple learning algorithms or instances into one, hopefully, more powerful predictor. And this is called ensembles. And ensembles are meta-algorithms, so it's an algorithm composed of multiple algorithms. And they aim to decrease variance, decrease bias, but ultimately improve predictive performance of different methods. Let's say if you train a KNN, you train a decision tree, they will inherently give different answers, but they might be measuring different things. And in combination, they might be stronger. And there are three basic approaches for ensemble methods. One is stacking, the other one is bagging, and the other one is boosting. And stacking, the basic idea behind the stacking is what I started describing. For the same data set. Instead of just training KNN and getting an answer, I'm going to train KNN, decision trees, SVMs, and so on and so forth. So I'm stacking multiple methods, and I'm getting the different answers from them, and then I get a majority voting to actually find a decision. So this has, the main idea behind this is each algorithm will have their limitations, but hopefully together they will be correct most of the time. So this is called stacking. So the same data, multiple different algorithms that will majority vote for the final decision. Okay? And this has been shown to improve performance in a few cases. Okay? Cons, well, you need to train multiple algorithms. And especially, let's say, if you use KNN, you need to optimize these parameters first, so it's a lot of computation involved. The other alternative is bagging. So different from stacking, in bagging, we are using the same algorithm. Let's say we have decision trees. But instead of using the same data all over again, so providing the full data set for different decision trees, which wouldn't make sense because they're going to generate the same model, we'll make different sets of the data, either using different data points or different features, right? So they are going to actually see different parts of the data, and hopefully will better focus on different aspects of the data. And this is the main principle of a method that's very famous and very, very efficient called random forest. So random forest will make random partitions of the data in terms of the data points, and the features we're using, instead of training one decision tree, we'll train hundreds of them, and then we'll then adjust or average all the results into a more robust approach. And is an approach proposed by Bremen in 2001. It's probably one of the most popular algorithms out there, one of the most robust, very popular, very effective algorithm that is available for classification and regression. It's very robust to outliers and also gives you by free feature selection. So random forest can tell you the importance, the relative importance of each attribute, looking at each of the individual decision trees. For instance, how often a given attribute is used on those trees is an indication of how important they are overall. And this is bagging. And just to finish off, boosting, the idea of boosting is starting with a not ideal model. So we have an initial data set. Let's say we train a tree, and we identified that we're trying to identify here apples, broccoli, and grapes. And we identified that your initial tree is not very good at identifying grapes and apples. So what we do is we generate a new set of data, and we train it again, but we prioritize the cases on which the previous algorithm was mistaken. Okay? So we give a higher weight for those cases that got it wrong. And then we get another tree. And then we repeat the process. We collect the bad cases and do it again. Repeat until it feels good, or repeat until you improve your performance metric. And that's boosting. Yeah? And that's it for today. On Friday, we're going to discuss different performance metrics, different validation approaches on how to go about and select the best performing model, making sure it's not overfitted. Thank you.